some logarithm properties to talk about. The goal over the next day or so is to develop a fluency and understanding of these properties so that when we get to equations, because this is the overall kind of reason we're doing these properties, and really the first 4 sections of this chapter are geared towards us being able to manipulate equations so we can easily solve them, so we can manipulate them in a way that it kind of takes the logarithmic or exponential equation and dwindles it down to like an equation that we've seen in Algebra 1 or Algebra 2. Okay? But we have to be able to understand some properties to be able to do that. One of the first things I want to talk about is what we've been dealing with in regards to the natural log. We've mentioned it a little bit on the last couple days. I just want to make sure that we specifically talk about it a little bit today. The natural log, I don't know, a long time ago somebody thought maybe writing log base e of x was too much. Okay? So they created the definition that whenever you're dealing with log with a base of e, instead of writing it that way, just write it ln. Okay? They mean the exact same thing. And to be honest with you, in your seats right now, if I were you, whenever I see ln, maybe the first several times I deal with it, until I'm comfortable with it, I'm going to change it to log base e every single time. Okay? Because the hope is that you have a little bit more familiarity and understanding of how to deal with log base of whatever. So we change log base e and just deal with that. Okay? Really, it tends to be a lot of confusion with people when we see ln. But it means the exact same thing we've been doing with log base 10, log base 2, log base 5, doesn't matter. Okay? E is just some number, right? 2.718, whatever. So I like to use that definition. Kind of give you an example of how we can use ln. Okay? We have a couple properties, and we've seen these properties earlier. Remember when we seen the property log base a of 1 is equal to 0? And we went through and said, well, if I take the exponential definition and logarithmic definition, the logarithmic definition, which means if this is true, or this is true if and only if this is true, we said that if we're in logarithmic form, we should be able to take a, raise it to the 0, and it comes back and gives me 1, right? A to the 0 is equal to 1. Well, when I write ln of 1 is equal to 0, these two things are saying the exact same thing, okay? Because a up here is just some arbitrary base, right? What's the base right here for ln of 1? E, okay? So what we're seeing here is that if I rewrite this as log base e of 1 is equal to 0, now apply the definition of a logarithm. E raised to the 0, anything raised to 0 is always 1. Okay? So that's kind of the proof of that property, that whenever you see ln of 1, you can automatically, quickly, if you've memorized it, you can change it to 0. Now, my hope is that you don't memorize it. My hope is that you use it enough, you recognize it enough, that it eventually becomes just common knowledge, right? Okay? Same thing happens then with some of these other properties that we saw with logarithms with base a. If I have ln of e, this one gets used a lot, okay? Ln of e is going to equate to 1, okay? But here's the logic behind it. I'm going to rewrite it as log base e, okay, of e is equal to 1. Does it make sense then that if I take and change this into an exponential, take my base of e, raise it to the exponent of 1, does that come back and give me my argument of e? Is e the first the same thing as e? Yeah, so there's the proof. Okay, and if you remember, that kind of parallels to, a couple days ago, the property was log base a of a. is equal to a 1. A raised to the first power comes back and gives me A. Okay? So there's some unique properties here that in dealing with just arbitrary logarithm or arbitrary basis for our logarithms, we learn 4 properties. Okay, with ln, we learn 4 properties, so 8 properties total. But my hope is that you really learn that ln is just one of those arbitrary bases e. Right? Does that kind of make sense? So you don't have to remember 8 properties; just remember 4, and you treat e like you treat any other base. Okay, so if I got something like ln of e to the x, that should give me x back. Okay, well, rewriting that then as log base e, so that's the ln part. I then have e to the x equals x. That's how we rewrite that. Now the proof of this then would be change it to an exponential. Take e as your base, raise it to that exponent, and it should come back and give me my argument, right? Do I get a true statement there? Yeah. Okay. So every time in proving why these properties work, we're trying to develop a true statement. The last one is, I think, probably one that is very useful. This one's pretty useful. Okay. You see here that if I have like basically what this one does for us eventually is if we're working in an equation and I have let's say that I have like in an equation e to the x is equal to, let's say, 12. Okay, I just kind of give you a little insight on where these things would be used. And I ask you to solve for x. Okay, well, what's really nice is that we can apply this property now, because I can do anything I want to the equation as long as I do it to both sides, right? So let's take the ln of this side and then take the ln of this side. If I do that, the left-hand side becomes ln of e to the x, right? Well, what do we say ln of e to the x is? It's just x. So we take that as x, and then the right-hand side became ln of 12, and ln of 12 is just a number, so we've solved for x there. Does that make sense? Okay. So that's the purpose of knowing some of these properties, is that they make equations in which we have variables and exponents. It makes them a little bit easier to solve. Okay. It's not easier to solve. It makes them solvable. Okay. That's the only route we can go to solve them, unless we use a graphical approach. And the last one, so that one gets used a lot, but the last one gets used probably the same amount, and it's when we have e to the ln of x. That ends up giving me just x as well. Now, writing in this one, we'd go e, and rewrite it as log base e of x gives me x. Okay. Now, this is in exponential form. Would you agree with that? We want to change that into logarithmic to see the proof of it. Okay. So I'm just gonna write what my logarithmic rule is. If I've got b to the y is equal to x, if and only if log base b of x is equal to y. That's the definition of a logarithm, right? Okay, so I'm just gonna put that underneath to see that we've got some correspondence in parts here. Would you guys agree that this this equation up here looks or matches, I guess, this one here? Would you guys agree with that in regards to format? Okay. Now I'm just going to talk about what corresponds, what matches up. Would you say that this E matches up with this B? Okay. So this B became the base on this side, right? So this E is going to become the base when I rewrite this thing into logarithmic form. Okay. This exponent here, would you guys say it corresponds to y? And then y jumped onto the other side of the equation over here, right? So up here, I'm going to let this exponent come over here. And then the last thing is that this x here corresponds to that x, right? Well, down here when I go from exponential to a logarithm, that x becomes the argument here, right? So I'm going to let this x become the argument there. All right? So we just figure out the things that match, okay, in the left-hand sides here and see where those components kind of show up in the logarithmic form. And we get this. Is that a true statement? So that's the proof to show that this is a true statement. E to the ln of x equals x. Whenever I see e to ln of x now, I can substitute it with x. All right? It just makes things so much easier to deal with. Okay? It allows me to do this. Let's say that, and we'll spend more time on this next week, but just want to give you a little bit of insight on where this stuff is predominantly used. If I have like ln of x is equal to 4, and I want to know what x is, the way I do that is I'm going to take this side, and I'm going to use e as a base. I'm going to raise the left-hand side as my exponent. Does that make sense? I can do anything to the left-hand side I want to. But then I have to follow the same thing on the right-hand side, right? Okay, so what that ends up looking like, it's kind of weird, I guess the font that I have there, but it would look like e raised to the ln of x is equal to e to the 4th. Well, what's e to the ln of x? Just x, right? So the x value that should go in here should be e to the 4th. Does that make sense to everyone? Okay. So those are the properties that we need to, I don't want to say memorize, just become accustomed to. Okay. I think there's some formats there that as you work through some problems, just the way they look, they might kind of trigger a memory to say, oh, that's one of those properties that maybe this thing will simplify to something a little bit easier that you can deal with. And then the more you see these then, the more they become just kind of second nature. They become common knowledge to you. I'm not saying go home and memorize them. There's nothing wrong with doing that. But I don't think you have to at this point. Okay, they're just going to be things that we use on a consistent basis when we solve these equations. We deal with these applications. If you think about some of the applications that we might use this stuff in later, just for instance, anything that grows is going to be exponential, right? And a lot of things that grow start with a particular amount. Let's just say an initial amount a sub 0, and they grow in regard, they show this nature of having e in them, okay? And then rt would be the exponent. That is, a very common kind of exponential growth process or formula. If you think about a sub 0 being an amount of money that you put into a bank account, that would be capital P, right? And we've had that formula, P times E raised to the RT. A lot of growth models exhibit that relationship there. But there will be times where we want to say, okay, if I started with, just like that question the other day, if I started with 300 mice, okay, and then after a particular time, I have, maybe after 3 years, I have 500 mice, can you find the growth rate? Well, the growth rate is an exponent, right? And the way that we would pull that exponent of r out is to use those properties that we just talked about. Okay, it makes things a little bit easier for us. So those properties are going to be used in regards to being able to solve for exponents that have our variables in them, or variable exponents. The next thing we want to talk about in order to be able to manipulate some equations to basically get in a situation to address what we were just talking about, use those properties. We have to learn that, and hopefully some of this stuff has already been taught to you. But if I have log base, I'm just going to use log base m of a times b. You guys remember last year talking about how that is log base m of a plus log base m of b? Ever remember doing that? if I have an argument that is a product for one logarithm, we can change it to a sum of logarithms with the same base of those individual factors, okay, a and b. I think it's beneficial to talk about why that thing is true, okay? And we like to be able to go both ways. We like to be able to start on the left-hand side and develop the right-hand side, or start on the right-hand side and develop the left-hand side, okay? If we start here and we want to go to that, we call that the expansion, okay? So we'll expand this logarithm. If we start on the right-hand side and we want to move down to just one logarithm, which actually inside equations, that's the route that will probably take the most. That's called condensing, okay? So we either like to expand these or condense these. Either way, it doesn't matter. But I want to explain to you why, okay? I think as you guys progress, I know some of you have talked to me that you have interest in math at the next level. And inside a lot of math courses at the next level, I'm not saying every single course, but there will be situations where they ask you to do proofs, okay? Now they may or may not be proofs that are, like what we did in geometry class, okay? That might be a good way to organize your thoughts and ideas, but a lot of proofs end up being early on algebraic, and then the further you get into those math courses, the more they become kind of theoretical, okay? So here we'll do an algebraic proof of why this is true, okay? First thing we're going to do, so this is the proof, and it's not too bad of a proof. It's all algebra. It might even be algebra 1 stuff, okay? And that's really what a lot of our properties come down to when you're in a textbook and you're reading a theorem, and they give you a property. Why does that property exist? Because behind the scenes, there's something like what we're about to do that proves why that exists, okay? So I'm going to, would you guys make the argument that if M, A, and B are just real numbers, okay? They can be anything they want to be. Obviously, A and B, we can't take logarithms of negative numbers, but let's just say that they're real numbers. If I take log, let's say, base 10 of 5, if I type that in my calculator, it's going to spit back just a number to me, right? So what I'm going to do is I'm going to say, let's let log base M of A, which is just a number, let's let it be X, which we're going to allow to be just a real number as well. Okay, it's a substitution that I think is going to make the algebra here a little bit easier. So we let log base M of A equal X, and let's let log base M of B equal Y. Okay. If I do that, would you guys agree that if I take this logarithm here, that I'm allowed to rewrite it in exponential form? I'm allowed to take the base M, raise it to the exponent of X, and that should spit back A to me. Do you guys agree with that? Okay, that's just using log base B of X equals Y, if and only if B to the Y equals X, right? That's the definition of a logarithm, and we're applying that right here to change that log into an exponent. Can I do the same thing here? M to the Y is equal to B. Then A times B, using the stuff that I've written here, A times B, would you agree that that is M to the X times M to the Y? Is that a true statement? A lot of times with proofs, when you're writing them in paragraphs, you use these transition words, then, thus, therefore, that kind of stuff, just to make it flow. I'm kind of terrible at choosing them. I choose then a lot. But would you agree that algebraically, if I multiply two bases together that are identical, what can you do with their exponents? Add them. So you're seeing here that a lot of this work is just Algebra 1 principles. Okay? So we get down to that, right? Okay? Now, here we used the definition, right? We used the definition to change to an exponential. Now, at this point, with this exponential, let's use the definition again to go back to a logarithm. If I go back to a logarithm, okay, so now we're on this side here, and we're going to go back to a logarithm. So this m becomes my base, right? Okay. The exponent moves to the other side of the equation. So the exponent becomes x plus y over there, right? And then the AB, that's my argument. Would you guys agree with that? So maybe I write, therefore. Okay. Now, substitute back x and y. What do we let x be? Yeah, x was log base m of a. What was y? Log base m of b. Does that prove the property that we start off with? Log base m of ab is identical to log base m of a plus log base m of b. Okay? So that's the algebraic, maybe analytical proof of that property. Okay? I think if you understand that, it gives you maybe a little appreciation of the property. It might allow you to use that property and understand that property a little bit better. But my main task here, my main concept, or I guess thought of showing you that was to recognize whenever reading a theorem that provides some property, some relationship, there is always something behind the scenes, whether it's that easy or it might be, exponentially more difficult. Okay, there's something going on in the back that allows that property to exist the way it does. Does that make sense, everyone? So when we do, and we could go through the proof. I think we're going to kind of run out of time if I do both these. If we go log base m of a over b, you guys remember that that's log base m of a minus log base m of b. Division turns into subtraction. Okay. I'll show you. I guess I'm not going to write it as a formal proof like the last one, but I think it does warrant maybe talking about this. Again, we go through the same process. We let x equal log m of a. Let y equal log m of b. Okay. So then we have log m of a over b is equal to x minus y, right? You guys don't need to write. I'm not going to ask you to be able to redo this. So if you don't want to write this down, you don't have to. You can always go back and watch the video if you want to put that in your notes. Now I'm going to change this to an exponential. So it becomes m Wait, I'm sorry. I don't know what's going on with my mouse today. I don't want to put it in exponential. I want to do this. I want to change these. Sorry, I messed up. I want to change these into exponentials. So m to the x is equal to a. M raised to the x is equal to a. And m raised to the y is equal to b, right? That's if you kind of parallel us to the last one we did, it's the same concept. Okay. We took this expression, changed it to an exponential. Take that equation, change it to an exponential. Now, would you guys agree that a over b? Okay, a over b, kind of what we did up here, a divided by b would be mx divided by my. I'm saying this wrong. M to the x divided by m to the y. Do you guys agree with that? Okay. Now, can we do this? If I have m to the x divided by m to the y, can I take that m to the y and put it in the numerator? But when I put it in the numerator, it's going to change that from a positive exponent to a negative one, right? And normally we don't like negative exponents, but it's fine. So now we got a over b. What do I do with bases that are the same? What do I do with their exponents? Add them. So I have x plus negative y. Well, x plus negative y is simply just x minus y. And there we stop with the exponent rules, and we go on and change this back into a logarithm. So this is my base, so I'll say log base m. Okay. This thing is my argument, so of a over b is equal then to that exponent of x minus y. But now if you remember what x minus y was, or what x was itself, x was log base m of a, and y was log base m of b. So when we have division, we can change it into subtraction. Again, ultimately, I would think that at least application-wise, we like to go from log base m of a minus log base m of b over to log base m of a over b. But because these are all equations, that's the proof of either way. Does that kind of make sense? Starting with the left-hand side, log of a over b is equal to log of m of a minus log m of b. If you reverse that, it's the same proof. The last one, if we had, you guys, oh, that's a terrible line. If you guys, kind of looks like your sketchbook. I'm just kidding. You got a good sketchbook. All right, so if we had, you guys remember this one? Log m of a raised to the c, that we can rewrite that as c times log base m of a. If we have an exponent, you can take that exponent out front and work from there. All right. Now this one, this proof is not as, I don't think it's not as hard, but it's not the same as the last two. It's not consistent. The way we approach this one, I'm going to put this in parentheses. But what we go through and we change this left-hand side. If I start with log base m of a raised to the c, that's going to be some number. So I'm going to let log base m of a to the c equal x. Okay? Now using the definition of a logarithm, we can say m raised to the x is equal to a raised to the c, right? Is that doable? All right, so now we do some manipulation of exponents that maybe initially doesn't make sense, but if we see the proof, we recognize that it was useful to do this. I'm going to raise both sides to an exponent. And that exponent is going to be 1 over c. Now the reason we do this is because it gets, if we think about what we have over here on this side, the a is raised to the first power, right? So the only way I can get this a to the c to be the first power is I raise it to a reciprocal power, right? Does that make sense? Because c raised to the 1 over c is what? 1. So I got a to the first. This side over here, I'm just going to rewrite this. I'm going to actually do the multiplication here. It becomes m raised to the x over c, right? Does that make sense, everyone? All right. So now, what we're going to do is apply the definition of a logarithm again and get back into logarithmic form. Well, if I do that, this is my base. So log base m of that, so that's my argument, should equal my exponent. Okay. Now let's solve for x. What would you do to both sides to solve for x? Multiply by c, so I get c log base m of a is equal to x. But what was x? Yep. We had letting that be log base m of a to the c. So you see then that manipulation of the exponents allows us to come up with that relationship, which is nice. It allows us to do a lot of nice things with exponents of logarithms when we start dealing with kind of pure applications of this stuff. All right, so in your homework, I know that took a lot of time to kind of go through those, but I think it's useful, again, to see proofs, okay? Because beyond, you're going to go to calculus, most of you, I would think, have the, I don't want to say, all of you have the ability to be successful in a calculus class. Beyond calculus, though, a lot of times, you still do calculations and all that good stuff, but there's also situations where you do a lot of proofs, and kind of open your eyes to that. When I was in high school, we didn't do any proofs until there's a little section in trig that you do some proofs. They're called identities, but I didn't really know what laid before me when I got into kind of the math programs and that major field. And I think it's a good idea to maybe see that if that's where I want to go, it just provides you a little bit of insight as you're taking other courses. You're trying to build information so that you can do proofs like that later on. I just wish that when I was in high school, I had a vision of the things to come, and maybe that would have taken or meant more as a student to me during those classes. Does that make sense? All right, if I knew 4 years from now, I'm going to be in a very proof-heavy course, then maybe it would have made me work a little bit harder in the current course, okay, to retain some of that information and understand the ins and outs of it a little bit better, instead of just being able to, people think math is just calculations, right? The further you get in math, it's a lot less calculations and a lot more theory, okay? But why do we need these properties? Why do we need these laws? I'm just going to write those again. So we have log base b of ab. That becomes log base b of a plus log base b of b. We had log base b of a over b, and that becomes log base b of a minus log base b of b. And then we had log base b of a to the c becomes c log base b of a. We have those laws or properties. I guess they call them laws. We want to be able to condense logarithms. So let's say that I have log base 4 of 2 plus log base 4 of 32. Now these laws only work if the bases are all the same, right? So that's the key thing here. The bases are both 4. Does this side here, does this expression look just like that? You got two things you're adding together, a and b, right? Logarithms are both 4. They're both the same base. So should I be able to take that and transform it, condense it down to something that looks like that? Yes. Okay, so this thing should equal log base 4 of 2 times 32, right? Now, you guys know 2 times 32, right? Log base 4 of 64. And we've now condensed it. We've condensed those two logarithms down to a single logarithm. And now because it's purely numerical, we can actually go through and actually see, maybe I'll let this be, I don't know, some variable, w, okay? 4, using now the exponential rule, 4 raised to the w is equal to 64. Well, what would w have to be So that when I take 4 raised to it, I get 64. 3. Okay. So the logarithm base 4 of 2 plus the logarithm base 4 of 32 is the same thing as 3. Okay. We can do that kind of stuff with both addition and subtraction. But usually, a lot of times, so in WebAssign in your homeworks, there'll be a couple where they're purely numerical like that. But there's going to then be some that are like this, where we got, log base 2 of maybe 6x. Okay? Now we're starting on this side. It's a product, right? And they're going to ask you, can you just rewrite it in expanded form? So I figure out what my factors are, and I rewrite this as log base 2 of one of those factors, plus then log base 2 of the other factor. Okay, so that expansion is a question that they'll often ask us to do. That's something we can do? All right, so it gets harder, obviously. If we've got, is this jogging the memory a little bit from what we've done last year? I'm just going to use, instead of changing the base here, I'm just going to use log base 10. But if I go x cubed y to the 6th, okay? Here you've got a product, right? X cubed and y to the 6th are being multiplied together. But you've also got exponents, okay? In this particular situation, what we want to do, because the exponents are kind of defined just for that x and just for that y, you want to separate this using this law first. So I'm going to go log of x cubed plus log of y to the 6th. Okay? Whenever I make an expansion, or whenever I condense it, I undo it to make sure that I've done it correctly. If I look at the right-hand side up there, that's log of a plus log of b, right? If I multiply those back together, x cubed and y to the 6th, do I get back to what I started with? Yeah. So I always, once I do a step, I always reverse it and see that I get back to what I started with. And that tells me that I've done this correctly. Okay? Now you've got basically two problems. Does that thing there look like that thing? When I got a base, my base is 10, but I've got something raised to a power, right? So can I take that power out front and write it that way? Can I do the same thing with the 6th power? So it's 6 log, 6 log y. Now, if you wanted to, you can factor a 3 out, but you don't need to. Usually when they ask you to expand things, factoring is not a requirement or a necessity. Let's do one more. Actually, we'll do, if time permits, 2 more. Let's use natural log. Is natural log any different? No, it's just a different base, right? Instead of base 10 or base B or base 5 or whatever, it's just base E. You don't need to change this to log base E. I think in expanding these things, that's kind of a waste of your time. Now you've got several things going on here. You've got a product, right? And you've got division, and you've also got that root. And we'll talk about what that means here when we get to it. But the division is what kind of dominates this problem. Okay? So I'm going to rewrite this as ln of AB minus ln of the cube root of C. And this is where I like to always go backwards. If I know subtraction just turns into division, right? So it means take AB and divide it by cube root of C. Does that get me back to what I started with? Yeah. So that tells me kind of the order of operations that I used here was correct. Now you've basically got two problems. You got this one here, which looks like that. So can I rewrite that as ln of A plus ln of B? And now I'm going to rewrite ln You guys remember roots are just another way of writing fractional exponents, aren't they? So I'm going to write that as c to the 1/3. What can I now do with that exponent of 1/3? Bring it out in front. So ln of a plus ln of b minus 1/3 ln of c. And we've now expanded that thing. And basically you're done expanding when you have no more products, you have no more quotients, okay, no more division, and you have no more exponents. Okay. On my website, I know we only did a handful of these examples, but on my website there's videos of, not me, but a lot of other people going through expanding and condensing these things. And I think the more that you see of them, the more that you do, you're going to get better at them. Okay? I am going to